Today in this video, we are going to study about aromatic halogen compounds of BSc Part 1 Organic Chemistry. Aromatic hydrocarbons form three types of halogen substituted derivatives. First are known as nuclear substituted. If hydrogen atom or benzene ring is substituted by hydrogen atom, then these compounds are known as aryl halides. For example, halobenzene, ortho meta or para halomethane, ortho meta or para ethyl benzene. Side chain substituted compounds. If hydrogen atom of the side chain of aromatic hydrocarbon is substituted by halogen, then these compounds are known as arylyl halides. For example, benzyl chloride or chlorophenyl methane, benzylidene chloride or benzyl chloride or dichlorophenyl methane, benzotrichloride or trichlorophenyl methane, 1-chloro-2-phenyl ethane. Third type of compounds are known as addition compounds. If three molecules of halogen add to three double bonds of benzene and its derivatives, then these compounds are known as addition compounds. When benzene reacts with chlorine or bromine in diffuse sunlight, it forms benzene hexachloride or benzene hexabromide. Now we come to the methods of preparation of aryl halides. These are different methods. First we'll take up is by direct halogenation by molecular halogen. Reactive benzene derivatives like aniline and phenol on direct chlorination and bromination form aryl halides. For example, aniline reacts with bromine aqueous form and form 2,4,6 tribromoaniline, whereas phenol reacts with aqueous bromine to form 2,4,6 tribromophenol. Second method we come to is benzene on chlorination in the presence of Lewis acids or halogen carrier like anhydrous AlCl3, SbCl5, I2 or ferrous forms chlorobenzene. If two molecules of chlorine are used, it forms ortho and para dichlorobenzene. For example, this benzene reacts with one molecule of chlorine in the presence of iron and FeCl3, it forms chlorobenzene. And when benzene reacts with two molecules of chlorine in the presence of Fe, it forms orthodichlorobenzene and para-dichlorobenzene. Similarly, when one molecule of bromine reacts with benzene, then bromobenzene is formed. Nitrobenzene on bromination forms meta-bromonitrobenzene. Toluene on chlorination with 1 mole of chlorine in the presence of sunlight in the presence of iron forms ortho and para chloro derivatives. So toluene reacts with halogen to form orthohalotoluene and parahalotoluene. Highly deactivating benzene derivatives on chlorination or bromination by chlorine or bromine in the presence of Ag2SO4 form aryl halides derivatives. For example, dinitrobenzene reacts with bromine in the presence of H2SO4 and Ag2SO4 to give 2-bromo-1,3-dinitrobenzene. The direct iodination of aromatic hydrocarbon is not useful reaction since the HI formed during reaction is a good reducing agent and it reduces the aryl halides back to aromatic hydrocarbons and iodine. Fluorobenzene cannot be prepared by direct chlorination of aromatic hydrocarbons since the reaction is very violent and cannot be easily controlled. Hence, only chlorination and bromination can be directly done, and iodination and for fluorination, specific conditions have to be implied. Next, we come to side chain halogenation. The most convenient method for the side chain substituted alkyl halides is by direct halogenation of aromatic hydrocarbons. For example, when boiling toluene reacts with chlorine in the presence of sunlight, benzotrichloride is formed. So, toluene reacts with Cl2, that one molecule of chlorine, and benzyl chloride is formed. It further reacts with second molecule of chlorine to give benzyl chloride which further reacts with third molecule of chlorine to give rise to benzochloride. When the side chain is large than the methyl group, then halogenation occurs on the benzylic carbon, that is the carbon atom, next to the benzene ring, and this is known as benzylic halogenation. So when ethyl benzene react with chlorine, then 1-chloro 1-phenyl ethane is formed. It further reacts with another molecule of chlorine to give rise to 1,1-dichloro 1-phenyl ethane. Then the second is by diazonium salts. In this we have a series of different reactions, and the first reaction we take is Sandomir reaction. Diazonium salt on treatment with corresponding halogens in the presence of cuprous halides forms nuclear halogen derivatives. This reaction is known as Sandomir reaction. In this reaction, the N2X group, that is diazonium group, is substituted by halogen atom, and the diazonium salt may be synthesized by nitro or amine derivatives. So this aromatic diazonium salt reacts with Cu2Cl2 in the presence of HCl, gives rise to aryl halide, that is aryl chloride, and reacts in the presence of Cu2Br2 and HBr and forms ArBr. If we see the mechanism, then we see then HCl reacts with CuCl to form CuCl minus and proton, and whereas ArN2 free radical reacts with CuCl2 in the slow step to give Ar free radical CuCl2 and N2, and this Ar free radical then reacts with CuCl2 to give ArCl and CuCl. Benzene diazonium chlorides may be obtained from nitrobenzene by the following methods. So nitrobenzene reacts with tin and HCl, undergoes the reaction and forms aniline. Then aniline reacts with NaNO2 in the presence of HCl at 273 to 383 Kelvin to give benzene diazonium chloride. If we come to the iodination, then iodobenzene is prepared by warming the diazo salts with potassium iodide, and we get iodobenzene. Third reaction we take is Bell's-Schiemann reaction. When benzene diazonium chloride reacts with fluoroboric acid, it forms benzene diazonium tetrafluoroborate. This benzene diazonium tetrafluoroborate salts are on heating forms bromofluoro derivatives, and this reaction is known as Bell's-Schiemann reaction. Next we come to the Bicatamin reaction. This is the modified reaction of Sandomir's reaction. In it, aryl diazonium salt reacts with halogen acids in the presence of copper, and with HCl it gives aryl chloride, and with bromine it gives aryl bromide. Next we come to Bihars-Dicker reaction. When silver salt of benzoic acid is heated with bromine in the presence of CCl4, it forms aryl bromide. By decarboxylation of halogenated sodium salts of benzoic acid. So halogenated sodium salt of benzoic acid on reaction with NaOH and CO forms aryl bromide, that is bromobenzene. Next we come to the reaction of preparation of alkyl halides by phenol. Phenol on treatment with PCl5 forms triphenyl phosphate and major chlorobenzene. So C6H5OH, that is phenol, reacts with PCl3 to give rise to C6H5Cl, and 3 molecules of phenol reacts with POCl3 formed in the first step, give rise to triphenyl phosphate. Next we come to bibenzene. Benzene on treatment with HOCl and HOBr form C6H5 chlorobenzene and bromobenzene. Now we come to the general properties of aryl halides. If we consider the physical state, then aryl halides are colorless, oily liquids or crystalline solids with specific odor, and their melting points and boiling points are more than their parent arenes. If we consider their solubility, then we see that aryl halides are heavier than water and they do not form hydrogen bonds with water, so they are considered insoluble in water but soluble in organic solvents like ether, benzene and CCl 4. Now we come to the nucleophilic substitution. Nucleophilic substitution and the structure of the halide. If we see the structure of the aryl halides, it resembles with vinyl halides because in both the compounds, the halogen atom is attached to the doubly bonded carbon atom. In vinyl chloride, three lone pairs of electrons are present on chlorine atom, which are in conjugation with CC double bond. So vinyl chloride has following two resonating structures. Due to the resonance, double bond character is developed in carbon-chlorine bond, and the bond length in vinyl chloride is 1.69 angstrom, which is lesser than CCl single bond length, that is 1.77 angstrom. Hence, CCl strength in vinyl halide is more than that of alkyl halides. With the result of this nucleophilic substitution reactions, SN1 and SN2 are more difficult in vinyl halides in comparison to alkyl halides. Similarly, for haloadenes, also show CCl bond length becomes 1.60, that is, in haloadenes, the nucleophilic substitution occurs with difficulty because in aryl halides, due to plus M effect, the CCl bond length becomes 1.60 angstrom, which is less than even vinyl halide. So to break this bond, extra energy is required, and hence aryl halides give nucleophilic substitution reaction with more difficulty than vinyl halides. Now if we consider, then we see, as we have seen before, the lone pair of electrons enter into conjugation and a double bond is formed between Cl and benzene carbon, and this double bond between C1 and C2 shifts on the second carbon, which becomes negative. Then by the successive migration of the double bond within the rings, the negative charge shifts from second position to the fourth position to the sixth position, and later the electron pair of the double bond, that is one double bond, shifts on the chloro group, and the electron pair at the sixth position shifts between C1 and C2, C6, and a double bond is formed between C1 and C6, and the neutrality is established. And in all these resonating structures, we see that the negative charge resides on second, fourth, and sixth position, whereas the chloro group becomes positive. That is, chloro group carries the positive charge. SN reaction in aryl halides proceeds with more difficulty than vinyl halides. They occur at comparatively high temperatures. For example, substitution of halogen atom by OH groups. So C6H5 reacts with aqueous NaOH at 613 Kelvin at high pressure to give phenol. It reacts with ammonia, aqueous ammonia, in the presence of Cu2O at 473 Kelvin at high pressure to give aniline. And if we see, it reacts with, that is, bromobenzene reacts with CuCN at 473 Kelvin in the presence of pyridine or DMF to give C6H5Cn. Now we come to the effect of substitution or nucleophilic substitution. It is observed that when electron withdrawing groups like NO2, NO, COOH, SO3H, CHO, COR are attached to the ortho or para, or ortho and para both positions to halogen atoms of aryl halides, nucleophilic substitution takes place comparatively at milder conditions. For example, if we consider chlorobenzene reacts with aqueous alkali in the presence of aqueous NaHCO3 and no reaction takes place. But if the same reaction is carried with 2-chloronitrobenzene, then the reaction occurs at 403 Kelvin to give rise to orthonitrophenol, and if the nitro group is increased, that is, now we use 1-chloro-2,4-dinitrobenzene, then this reaction occurs even at lower temperature, that is 373 Kelvin, and we get 2,4-dinitrophenol. And if the third position of ortho, that is, if the ortho position, both ortho positions are occupied, that is, we take 1-chloro-2,4,6-trinitrobenzene, then the temperature gets even lower, that is, the reaction takes place at 308 Kelvin and 2,4,6-trinitrophenol is formed. So we see that with chlorobenzene no reaction takes place. At ortho position nitro is there, the reaction takes place at 403. If the ortho and para position both are occupied by electron chloride group, then the reaction temperature decreases from 403 to 403 Kelvin to 373 Kelvin. to give the reaction product, and if both ortho position and the para position is occupied by the electron withdrawing group, then we see that the reaction temperature decreases further from 373 to 308 Kelvin and the product is obtained. This is all for today. Thank you.